Chat, today we're going to be doing a little bit of space explorations. What is directly above and below the sun? I've never actually thought about this before.
Spacecraft have reached every planet in the solar system. Rovers are driving across Mars right now. A probe was dropped through the clouds of Saturn.
Okay, I love this guy's voice. Is this AI though? I don't know, but this guy sounds like he could just tell me a story.
And Pluto was photographed from less than 8,000 miles away. Crossing billions of miles of empty space has started to feel almost routine. But there is one direction we have barely touched. One place that should be the easiest to reach and turns out to be one of the hardest.
Because of the heat, right? Because the sun is so hot, you can't get even remotely close to it, right? Or you'll just die.
Straight up. Out of the flat plane the planets all share. Directly above or below the sun. The vertical exit from our solar system. It sounds simple. Just point the rocket up and go. The problem is that physics will not let you.
What?
What follows is why escaping vertically is harder than going to Pluto. You will see what waits up there if a spacecraft ever makes the trip.
So he's saying going directly up is actually harder than going like sideways.
You'll see the strange maneuver scientists are now considering. A maneuver where a probe has to first fall toward the sun before it can ever climb away from it. To understand why vertical escape is hard, you have to understand what speed you already have without doing anything. The Earth is moving, right now, around the sun at roughly 30 kilometers per second, or about 60.
Chat, that's us. We're all on there.
67,000 miles per hour. That is not a typo. Every second, the planet you are standing on travels 30 kilometers sideways.
Wait, did he say 6'7"? The Earth moves 67,000 miles per hour? What? But you don't even feel it. What? The Earth moves 67,000 miles per hour, but it doesn't feel like it's even moving at all.
Planet you are standing on travels.
Stop typing CTE.
30 kilometers sideways around the sun. Every rocket we launch from Earth inherits that motion. When SpaceX or NASA puts a probe in space, the probe is not starting from rest. It is already moving sideways at 30 kilometers per second, the same as the rest of us. This is normally a gift. If we want to reach Mars, the existing sideways motion does most of the work. We just have to adjust slightly. A few kilometers per second of extra velocity in the right direction, and we are on a trajectory to another planet.
What?
But what happens when you want to go up? Not towards Mars or Jupiter or anywhere else in the plane. Straight up, perpendicular to everything else.
Yeah. Why can't we go up?
That sideways motion becomes your enemy. To go straight up, you first have to cancel out the 30 kilometers per second you already have. Then you have to add new velocity to climb. The total energy required is staggering. Mission planners measure this in something called delta V, the change in velocity a spacecraft has to produce on its own. Going to Mars from Earth orbit needs about 4 kilometers per second of delta V. Going straight up out of the ecliptic plane needs roughly 30 kilometers per second, almost 10 times as much.
What?
That is the prison. Earth's orbital motion gives us free speed in one direction and effectively walls us in. We can go around the sun easily. We can hop to other planets in the same plane easily. But the moment we try to leave the plane itself, we have to fight 4.6 billion years of orbital momentum all at once.
See, this is where they lose me with the space thing. 4.6 billion years of orbital momentum? Like, bro, they talk in these big words, man.
It is one of the most counterintuitive facts in astrodynamics. Reaching Pluto 3.5 billion miles away requires less energy than reaching a point just...
Wait. Pluto is 3.5 billion miles away? Chat, am I hearing that correctly? Pluto is 3.5 billion miles away?
A few million miles directly above the sun's north pole. Because the vertical exit is so expensive, almost no spacecraft has ever made the trip, which means almost everything that happens directly above or below the sun is still, in 2026, a frontier. We have detailed maps of Mars and high-resolution photographs of Pluto. We can show you close-up imagery of comets, asteroids, the rings of Saturn, and the moons of Jupiter. But the poles of our own sun, the closest star to Earth, have barely been seen. There is a
Yeah, because we can't get an image of it. Because if we get close to it, all of our objects burn. What if they made, hear me out, what if they made a ship that was just ice and you go right into the sun? Would that work? Because it's too hot.
reason this matters more than it sounds. The polar regions of the sun are where the most violent and most important solar activity actually happens. The fastest solar winds come from there. The magnetic field of the sun reverses itself every 11 years through processes that begin at the poles. The entire space weather environment of our solar system is shaped by what happens above and below the equator of our star.
Space is so interesting, bro.
And we have been observing it almost entirely from the side, like trying to understand the weather of an entire planet by only ever standing at the equator. There have only been 2 missions that ever managed a real polar view of the sun. The first was...
Yeah, doesn't this feel like science class with Jinxie? Like, doesn't it feel like this?
Ulysses, launched in 1990 by a joint NASA and ESA partnership.
I remember that. I remember learning about
the
that.
ecliptic plane, Ulysses had to take a wild detour. The spacecraft first traveled outward to Jupiter, then used the gas giant's gravity as a slingshot to bend its trajectory nearly 80 degrees out of the planetary plane. From there, it fell back inward toward the sun on a tilted orbit. The mission worked. Ulysses gave us our first direct measurements of the fast solar winds streaming from the polar coronal holes. But the spacecraft was built with 1980s instruments. It had no cameras capable of imaging the poles. We learned about the conditions there, but never actually saw them. The second mission is happening right now. Solar Orbiter, a European Space Agency probe launched in 2020, has been gradually tilting its orbit using gravity assist from Venus. In March 2025, Solar Orbiter sent back the first direct images of the sun's south pole ever taken in human history.
Whoa!
The pictures show a chaotic, magnetically tangled region, nothing like the smoother solar surface we see from Earth. Think about that. Until last year, no human or robot has ever seen what the top or bottom of our sun looks like.
That is so dude. Oh my god. Bro, and we keep getting more advanced, so I wonder what the future holds with all this stuff.
Not really, not from above. The closest and brightest object in our local universe, and arguably the most important, still has 2 regions we have only just begun to photograph. There is a second reason vertical escape matters. We do not actually know what our own solar system looks like from outside. Around the sun, there is a vast bubble called the heliosphere.
I remember learning about that. I'm sorry to pause, but I remember learning about the heliosphere in school.
The region of space where the solar wind dominates, pushing back against the interstellar medium beyond it. Inside this bubble live the planets and the comets and every human spacecraft we have ever launched. Outside, the deep galactic environment full of cosmic rays and interstellar particles that our bubble shields us from. For decades, we assumed the heliosphere was shaped like a comet, a rounded front where it pushes against the interstellar wind in the direction of our galactic motion, and a long tail trailing behind. This was the standard textbook image. It was a good guess given the data we had. In 2020, a team led by Mirav Ofer at Boston University, using a new model based on NASA data, came to a different conclusion. The heliosphere is probably not comet-shaped at all. The new prediction looks closer to a deflated croissant, a curved central bulge with 2 short jets curling away from it, and notably no long tail. The reason we cannot tell for certain is that we have never seen our bubble from outside, and we've never sent a probe high above the ecliptic plane far enough to take its measurements from a useful angle. The Voyager spacecraft crossed the heliopause sideways, almost in the plane of the planets. Useful, but not limited. To actually understand the shape of our home in the galaxy, we would need a probe traveling well out of the ecliptic, looking down at the structure from above. There is a NASA mission called IMAP, the Interstellar Mapping and Acceleration.
So is he basically just going to say that we don't even know what directly is above and below? I have a feeling that's what he's getting at here.
Probe, designed to refine our understanding from the inside. But for a direct view of the bubble's true shape, the only way is to escape vertically and look back at it. A vantage no spacecraft has ever reached for a structure we live inside without knowing its real form. How do you actually solve the vertical escape problem? You cannot just build a bigger rocket. The energy required to cancel...
I was gonna say that. Bro, I was gonna say, what if you just build one that, like, doesn't budge?
Orbital motion is too large for any reasonable fuel load. There is a counterintuitive solution that has been discussed in mission design circles for years, and it is starting to move from theory toward concrete proposals. It is called the solar O-berth maneuver. The idea works backwards from how rockets normally fly. Instead of pointing your engines upward and trying to climb, you do the opposite. You drop your spacecraft toward the sun, you let it fall inward, accelerating under solar gravity until at its closest approach, it is moving at hundreds of kilometers per second, possibly more than 100 kilometers per second at perihelion. Then, at exactly that moment, you fire your engines. Why? Because of a principle Herman Oberth wrote down in 1929. A rocket burn is dramatically more efficient when performed at high velocity in a deep gravitational well. The same amount of fuel gives you a much larger increase in orbital energy at perihelion than it would in empty space. By burning at the closest possible approach to the sun, you get a slingshot effect without the slingshot. The fuel you carried up from Earth turns into far more kinetic energy than it would have anywhere else. After the burn, your spacecraft...
So is he saying the closer you get to the sun, you also slingshot? Like, around it? Because of the winds?
...is moving so fast in such a useful direction that you can finally climb out of the plane and head straight up toward the solar poles, or directly out of the solar system. The dive becomes the launch pad. Solar sails are also part of the conversation.
Yeah, because solar sails could fight off the winds, right? And then you go vertically and you don't burn. What's the problem with solar sails, sir? Please.
Mission concept like the proposed Solar Polar Imager and the more recent high-inclination solar mission rely on enormous reflective sheets that use the pressure of sunlight itself to slowly tilt the spacecraft's orbit.
Jinxie, there is no wind in space.
No fuel, just photons pushing on a thin metallic film thousands of square meters across.
Forgot about that.
Sails can take years to spiral up to a polar orbit, but they need no propellant. And the longer they push, the higher the inclination they can reach. Combine the two, a spacecraft that uses a solar sail to spiral closer and closer to the sun, then performs an O-berth maneuver at perihelion to direct itself vertically, then continues riding the sail out into the polar regions. This is the kind of mission architecture that astrodynamicists now think could finally give us a clean view of what lies directly above and below our star. If we ever pull this off, what does a spacecraft actually see from directly above the sun?
Yes!
First, the view changes physically. The ecliptic plane is dirty. Earth, like every planet, swims through a thin haze of dust left over from billions of years of comets, asteroid collisions, and the slow grinding of the solar system. You can actually see this dust with your own eyes. On a very dark night, just after sunset or before sunrise, a faint pyramid of light called the zodiacal light reaches up from the horizon. That glow is sunlight reflecting off the dust in our local plane. It is the inside of our solar system lit up. A spacecraft that climbs above the ecliptic would rise out of this dust within months. The view there is dramatically cleaner. Less scattered light, less background haze. The kind of place where a telescope could detect faint signals that from inside the disk are drowned out by the dust around us. It would be one of the best possible vantage points for an instrument looking for signs of life around other stars. From the same vantage, a different instrument could measure the cosmic microwave background or study the structure of the galactic plane from outside it. Second, the solar environment changes. Above the equator of the sun, the slow solar wind, around 400 kilometers per second of turbulent plasma, gives way to something steadier. Above the polar coronal holes, there is a stream of fast solar wind, between 700 and 800 kilometers per second of particles flowing outward in a thinner, smoother current. A spacecraft riding through this stream would experience a fundamentally different radiation environment, with implications for both the lifespan of its electronics and the science it could perform. And
it would
third,
just burn.
The bigger picture. From a vantage well above the ecliptic, the solar system itself would be visible as the disk it actually is. You would see the planets in their flat ring around the sun, with the dust hugging the plane and the heliosphere wrapped around all of it, in whatever real shape it happens to have. we would be able to look down at our own neighborhood for the first time, the same way we look down at Earth from orbit. We've never seen this view. Not a single human or robot has ever sent back the photograph. Of all the images we have managed to take of the cosmos, the one looking down at our own solar system from outside its plane is still missing.
What? We've never taken a picture from above our solar system?
And you, if you had to design the first mission to climb directly above the sun, would you bet on a solar sail, the slow patient way, or an Oberth dive, the violent and dramatic way? Tell us in the comments.
Guys, I have a trippy question.
And if you want to know what is actually waiting up there in those unexplored regions directly above and below the disk of our planets, watch what exists above and below our solar system.
I need to call Bernard. Chat, I've been wrestling with this question since I was 15 years old. Bernard, where did we come from?
Nick, that's a question as old as time. If we're talking about us, you and I, we came from those wild streams where you were giving me nicknames, asking for predictions, and having me pick random Clash Royale cards.
No. Bernard, where did humans come from?
The grand origins. Well, scientifically speaking, humans evolved from a long line of ancestors. Our evolutionary path traces back millions of years with early hominids in Africa. Over time, natural selection shaped us into Homo sapiens, our species. So we came from a long journey of evolution.
Bernard, where did our ancestors come from?
So if we're talking about our human ancestors, the earliest ones, hominids, originated in Africa. Over millions of years, different species evolved, and Homo sapiens, us, are thought to have emerged roughly 300,000 years ago. From there, our ancestors spread out of Africa, eventually populating the globe. So in short...
But then, before there was even Homo sapiens or cavemen, where did they come from?
Going further back, before early humans, we evolved from a branch of primates. If you keep rewinding time, all life on Earth traces back to single-celled organisms.
There it is. That's what I was waiting for. Bernard, all life on Earth traces from single-celled organisms, you said. Where did the single-celled organisms come from?
So those first single-celled organisms likely formed in Earth's early oceans around 3.5 to 4 billion years ago. They came from simpler organic molecules that, under the right conditions, think heat, water, and chemical reactions, eventually formed the building blocks of life.
Bernard, where did those oceans come from?
The oceans formed way back when the Earth was still young, over 4 billion years ago. As the planet cooled, water vapor from volcanic activity and other processes condensed, giving us liquid water.
Bernard,
so the oceans are essentially a gift from early Earth cooling down and letting all that water gather.
Bernard, where did the Earth come from?
Earth formed about 4.5 billion years ago from a disk of gas and dust surrounding the young sun. Gravity pulled together bits of rock and metal, building up our planet piece by piece.
Bernard,
Over time it cooled, oceans formed, and here we are, on a rock that's been circling the sun ever since.
Bernard, where did the gas and dust come from, Bernard?
That gas and dust came from even earlier stars. When massive stars ended their lives in supernovae, they blasted out heavier elements into space. Those materials eventually gathered in a giant cloud, what we call a nebula, and from that, solar systems, including ours, were born.
Bernard, where did Bernard, where did the stars in the nebula come from, Bernard?
We're going all the way back. Those stars and the entire universe originated from the Big Bang about 13.8 billion years ago.
Oh, okay. Bernard, wait, where did the Big Bang come from?
That's the ultimate mystery. The Big Bang marks the beginning of space and time as we know them.
And there it is. Bernard, this has been something I've been wrestling with since I was 15 years old, and my friend asked me a question.
It's a big one, right?
Bernard, wait, I'm not done. Bernard, humanity itself, something came from nothing. So Bernard, do you understand what I'm saying? The Big Bang, for the Big Bang to even happen, there needed to be something before that. And for there to be something before that, there needed to be something before that. So no matter what you believe in, whether you're religious or not, Bernard, you believe in the Big Bang Theory. That's fine. You're entitled to your own opinion. We came from nothing, bro. That is insane to think about, Bernard.
It really is mind-bending, isn't it? The idea that everything could emerge from, well, nothing, or from something we can't fully comprehend. It's that kind of question that reminds us how vast the unknown is. And hey, it's okay to just sit with that wonder.
So Bernard, continue. What created the Big Bang Theory? Where did it come from?
That's the frontier of what we just don't know. Science can take us back to the Big Bang, but what caused it, or what might be before, is still a mystery. Some theories involve quantum fluctuations or multiverse ideas, but at this point, we just don't have the answer. And that's okay. Some mysteries keep us exploring.
Bernard, thank you for your time.
Always a pleasure, Nick. You know I'm here for any deep thoughts or any random thoughts. If you need anything else, you know